Assalamu alaikum. Let's come to one more numerical, which again from the assignment first. In this case, it's actually a double circuit transmission line, where usually we solve the double circuit transmission line in the class that were in the hexagonal form, but this is the one which is in the form of the in which all the conductors are placed horizontally on a tower. You can see that they are apart from each other only 1 meter. And why I gave you this problem, just to uh, make you sure that there, in case of bundle conductors, where the distance between A and A dash as compared to distance between the phases between A, B and C was very small, but in this case that is not the case. You can see they are intermixed, so all the distance ought to be taken care. So we'll first calculate. It's given that the distance between the individual conductors is 1 meter and the radius of each conductor is given as 1.5 centimeter. So we need to calculate first, as we did in case of double circuit line. We need to first calculate the self GMD. For self GMD, we need to calculate dA, dB and dC. dA, dB and dC, and then take the cube root of them, multiply them and then take cube root of them. First we will calculate dA. dA, we know that the self GMD of phase A, that is conductor A and A dash, it is the square root of R dash into dA dash, and R dash is equal to 0.7788 into 1.5 10 raised by minus 2, and the distance between A and A dash is 1 plus 1 plus 1, 3 meter. That comes out to be this. You can see that A and A dash, B and B dash and C and C dash, they are symmetric. That means the value of dA will be equal to dA will be equal to dB will be equal to dC. When this is equal, it means this, that's written over here, dA is equal to dB is equal to dC. That means ds will be equal to cube root of dA into dA into dA, that is simply equal to dA. So I calculate only dA, that is equal to 0.1872 meter. Similarly, the mutual GMD, that is DM, it is actually mutual GMD. So DM is equal to cube root of DAB, DBC, DCA. This has been also explained in the class in detail. So DAB is the distance between A and B, that is AB, DAB, DAB dash, DA dash B, DA dash B dash. So DAB is equal to 1 meter, DAB dash, 1, 2, 3, 4, 4 meter, DA dash B, A dash B is 2 meter, and dA dash B dash, that's again 1 meter. So it will be equal to 4th root of 8. Similarly, DBC is equal to 4th root of DBC into DBC dash DB dash C into DB dash C dash, that is equal to 4th root of DBC BC, that's 1 meter, DBC dash BC dash, that's 4 meter, DB dash C that is 2 meter, and dB dash C dash, that is 1 meter. Actually this A and B and C, they are actually very symmetric to each other. It will be same. I will calculate for it. It will come out to be again 4th root of 8. Now DCA will be equal to DCA into DCA dash into DCA C dash A into DC dash A dash. It will be equal to 4th root of DCA. C and A, the difference is, or their distance is 2 meter. DCA dash C dash is 1 meter, DC dash A C dash A 1, 2, 3, 4, 5 meter, and D C dash A dash is 2 meter. It comes out to be 4th root of 20. So finally, this L is equal to 2 into 10 to the minus 7 dm by ds, where dm is equal to cube root of dab dbc dca, that comes out to be equal to 1.8152 meter. Then L is equal to 2 into 10 to the minus 7 dm by d, it comes out to be 0.455 millihenry per kilometer. I hope you understood. This was a very simple problem. One more problem that I have chosen is from question number 4. It is from the performance of the transmission line. In this case, it is given that Vs is equal to 220 kV, that is the sending end voltage, not receiving end voltage. Load at the sending end is 60 MVA at 0.8 power factor. 0.8 power factor. B is equal to 20 plus J140 and A is equal to 0.93 plus J 0.016. So in this case we are asked to find out the value of VR. This is a slightly different problem, but it is very easy. We know that this Vs is equal to AVR plus BIR. From this equation we can get the value of this VR. We know the value of A, we know the value of B, we know the value of Vs. In this equation we don't know the value of VR and IR. VR we can simply get from this equation, because SR is equal to, that is the apparent power at the sending end. Apparent power at the sending end will be equal divided by the voltage at the receiving end will be the current at the receiving end. It is equal to 6 into 10 to the power 3 divided by VR. Since it is in MVA, actually it should have been 6 into 10 to the power 6 divided by VR into 10 to the power 3. That 10 to the power 3, 10 to the power 3 will cancel out. That means I am considering this VR in terms of kilowatt. But when this calculation is done, overall unit of this quantity will be ampere. So when I use this, but you have to use this in phasor form. Until and unless you don't do this, you will not get the exact value. So here, so Vs is equal to 20, but an angle of delta, because power will flow from sending end to receiving end, and that only when there is a phase angle lead from sending end to receiving end. And I am assuming that angle to be delta. It is equal to 0.93 plus J 0.06 into VR at an angle of 0. We are assuming this VR to be reference and Vs at an angle of delta to it, plus 20 plus J140, because this is AVR, B is this value, IR we have just now calculated, 60 into 10 to the power 3 divided by VR, just forget about this for the time being, at an angle of minus 36.86, because IR is at 0.8 power factor lagging. It's given as IR is given as 0.8 power factor lagging. Now you can see it, this 220, it is actually kV, that means this term is in kilovolt. Since this VR we are assuming it to be kilovolt, this term will also be in kilovolt. Now this is actually in ohms multiplied by current, it will be in voltage. So to make it into kilovolt, we divide by 1000 to it, it will come out to be kilovolt. That 1000 and this 1000 will cancel out now. So on proceeding, you will see that I will write down it in the rectangular form. It will be equal to 220 cos of delta plus J 220 sine of delta plus 0.93 plus J 0.016 into VR, because VR will not have any imaginary part, its angle is 0, plus I just what I did in this case, I just multiply these three terms. One is this term, this term and this term, actually one angle minus 36.1, and then separate real and imaginary part, it comes out to be approximately equal to 6000 plus J 6000. It may be slightly different, it may be 5991 and this may be 6001. I write it down as 6000 and 6000, so to make the calculations easier. Now equating real and imaginary parts, in this case it is 220 cos of delta is equal to 0.93 VR plus 6000 divided by VR, and this is the real part, 0.93 into VR plus 6000 divided by VR, and 220 sine of delta, this imaginary part, is equal to 0.016 VR plus 6000 divided by VR. Actually these are two equations with two variables, because here one variable is delta and another variable VR. we're only interested in the value of VR, so we will eliminate this delta. How we will eliminate? We'll square and adding these two terms. It will be 220 square into cos square delta is equal to this whole term square. This will also be 220 square sin square delta is equal to this whole term. Then we add these two terms. So when we add, this will be 220 square cos square delta plus 220 square sin square delta, and then 220 square will be taken out as common. Sin square delta cos square delta will be equal to 1. It will be automatically eliminated. Then the equation becomes 220 square is equal to 0.93 VR plus 6000 divided by VR square plus 0.01 into 0.016 VR plus 6000 divided by VR ka whole square. So when we solve this equation, we get VR to be equal to 202 kV. Definitely this has to be less than that of the sending end voltage. So usually these type of problems are in such a way so that receiving end voltage is given. In that case, it is very simple to get the IR and then put the equation over here. We get the VS. So we'll get VS as well as delta. In that case, it is that type of problems are usually given, and that are slightly simple. But this type of problem is also simple, but you have to take care how to deal with this, and you have to deal with the two variables in this case. Okay, thank you.